George, can you share your screen?
Here, yeah. Give me a second. I will get to it. Okay, so. Okay, do you see the slides?
Okay, thank you. Thank you.
Okay. So thank you very much for inviting me, and congratulations to Rafail Khasminskii for his 90th birthday. It's a big moment, and I appreciate very much having this opportunity to speak here. I'm going to speak on a topic in imaging, which has been something I've been working on for more than 20 years now. This is some joint work with Miguel Moscoso, Alexei Novikov, and Chrysula Tsonga, which is it's a paper, this is what I'm going to discuss, that appeared last year. I chose this even though it's not very much related to things that I have done over the years that connect with Rafail's work. But I thought there's some contrast there that I will return towards the end and make some qualitative comments, how they're not really related, but they have an interesting history. So let me begin by discussing the introducing and discussing the outline of what I'm going to say. First of all, I'm going to try to be a bit more explicit regarding imaging, because I assume that that people, the people I'm speaking to in this community, may not know the background in imaging, and I think I will spend a little bit of time on that, just to make sure that you understand what the issues are before I state what the results are. Okay, so until fairly recently, imaging or image formation from recorded data, which I will show a schematic in a bit, has been mostly done with a least squares optimization, completely straightforward least squares. This produces images that are not very sharp, but they're also not affected so much when the data is noisy, even quite noisy. In other words, the L2 method, which is what has been used by engineers and physicists, overwhelmingly.
Sorry, George, have you changed pages? Because we are still seeing the first page.
I did change.
Yeah, so there is a problem with the share. Maybe you share another window and we see another window, in fact.
Okay, what you don't see my, okay, let me just go out. Do you see this one now?
Yes, now we.
Now you see it. Do you see it changing now?
Yeah.
Okay, good. So I'll leave it like that. I had put the whole screen, but that doesn't work so well. Okay. So I was just reading the first paragraph here, how the L2 theory is just what is being universally used, and that it's very sharp. Now, when the image has sparse support, in other words, most of the feature vector that we're trying to image, most of its components are zero. That's what's called sparse, and then L1 optimization can produce very sharp results, even exact images. This is something that was articulated very precisely more than 10 years ago, 15 years ago, but the idea that L1 optimization really produced sharp images was known even earlier, before than that. So a lot of the applied research in this area switched to L1 optimization to obtain images about I would say about 10 years ago. So what I want to do is I want to begin by reviewing briefly the imaging problem and how the physical imaging problem can be reduced to solving an underdetermined linear system. Then I will say what L1 and L2 optimization amounts to, which is straightforward. Then I'm going to introduce this new idea of the noise collector. And then I'm going to show some numerical results. The noise collector is a way to actually denoise the image. And then there are a couple of theorems that there are really more than two, but I will state two because that's enough for the discussion to see what the idea is. And also, I will end up by pointing out that there are some other unexpected applications of this noise collector idea, but there are also some problems that we've been struggling with for which we don't have an answer, and I want to end up with the discussion of these open problems. So let me go to the imaging problem with a schematic, and this is what we have. It's not the scattering problem, but it's the source problem. So I have an array of sensors on the left. These dots are receivers. They assume to be small, that localized receivers, and their location is denoted by x sub bar, the vector x sub bar. The linear size of the array is A, and the spacing between the sensors is h. Usually the h is very small, it's smaller than the wavelength, and A can be large. You can have a lot of receivers on the array. Capital L is the range, is the distance between the array and the image window. The image window is this dotted box here, which we don't know inside the image window where the sources that we're trying to locate. We don't know where they are, but we believe we're testing inside this window to find out where they are. So the real locations of the sources are denoted by Zj. The wavelength is lambda, the typical wavelength. Usually the signals are broadband, there are pulses. So there's more than one wavelength, but this is the typical wavelength. And this window, the image window, is pixelized. In other words, there's a distribution of points that we put inside here where the scatterers could lie. I mean, we don't know that the actual the source locations might not be exactly on the pixels that we choose. So there's a small issue there, whether they're on the pixels or not, but I will ignore that. I will assume that they are in fact on the pixels. And then the issue is how do you pixelize? And once you have pixelized, how do you find which of these pixels are the ones that have the sources whose signals you're recording on the array? So to review, we have the following scales, which is the linear size of the array A. We have the range capital L and the typical wavelength. And the physics of the problem says that typically with these three parameters, the resolution that we expect in finding out where these unknown source locations are should be of the form lambda capital L over A. In other words, we know from physics that what resolution to expect inside the image window. That tells us more or less what the pixelization should be. And then the receiver locations of the array are at XR, and the unknown source locations in the image window are the ZJs. That's what we have. Okay, so that's the actual, and this is called passive imaging setup because, of course, the active imaging setup would be where I actually emit pulses from the array, and then these objects here are not sources themselves, but they are scatterers. Going from the passive to the active is not very complicated. So very much all the methods that I'm describing here, everything that I say here can be immediately carried over, especially the L1 methods can be carried over to the active imaging setup with not much difficulty. Okay, so here's what I'm gonna model now the signals received. And for that, I'm going to assume that the medium is homogeneous. In other words, between the sources and the array, the medium is completely homogeneous. Okay, so the waves, which are pulses, are emitted from the sources and are recorded at the receivers. For simplicity in discussing what I'm presenting here, I will assume that we're dealing with a single frequency. In the numerical simulations, there are many frequencies, so that you have a pulse. So I denote by capital G of x, y, omega, the Green's function for wave propagation for the ordinary wave equation at circular frequency omega, going from the point y, which is in the image window, to the point x, which is in the receiving array. And then I form a vector of these Green's functions, where the vector is indexed by a point y in the array. And then this vector, which is of size capital N, is simply the Green's function evaluated at each point on the receiving array. So there are capital N points in the receiving array. And this Green's function, which is written below, this is the three-dimensional Green's function for the wave equation. It's written right here. And C0 is the free space speed of sound, speed of wave propagation, if it's sound, or it could be light, anything. That's what it looks like. And then that's what you have is this complex exponentials divided by the distance from the point in the image window y to the point on the receiving array. This, you string them all out and you form a vector. And then the signal that the data, the model for the data that you are receiving is simply the sum of the signal emitted at Zj, received at XR, and this is the strength of the signal emitted, and you sum from j equals 1 to m, where capital M is the number of the unknown number of sources. So what is unknown here in this data, you record this data at the frequencies and at different frequencies if you have more than one frequency, and at the different points XR. What you don't know here, what you would like to find from this data, is which are the points Zj in the image window that emit it, and what are the strengths of the sources, the alpha j. So in order to emphasize that those are the unknown here, I write this in a generic form where the summation is for all locations in the image window, pixels in the image window, from j equals 1 to capital K, where capital K is much bigger than this M, and that runs over all the pixels inside the image window. And then this vector, the strength of the source vector rho j, in reality, has a lot of zeros, and it's only where it's not zero that it's equal to alpha j. And of course, the support of this vector is exactly the location Zj of the unknown sources. So that's what the objective is. We have this B that we measure, that we record, and then from the structure of the rho and its support in particular, we're trying to recover where the location is and what's the strength. So let's see. This what I just wrote here, the B equals rho j, the sum of the rho j times the Green's function here. I can write it in as a linear system, where A is this matrix whose columns are these vectors of these G's here. This G here becomes a column for each Y. And so I have this matrix A, which is an n by k matrix. N is the number of receivers, k is the number of pixels in the image window, equals B. This is the data. And AK, the columns of A are the single frequency Green's function vectors normalized to have length 1. I didn't normalize it before, but when we actually do the analysis, we normalize. What I wrote before wasn't normalized. And the system A rho equals B relates the unknown vector rho, the source vector or the reflectivity vector if it was active imaging, to the data vector B. Okay. It is a support of this vector that is most important to determine. And here, n is usually very large, k is even much larger, so the system is underdetermined. In other words, you have more unknowns than you have equations. That's what k is a number of unknowns. And we're assuming that the support of the unknown vector m, the size of the support, is much smaller than k. In the L2 theory, we look for the minimum L2 norm solution of this linear system. In other words, I will say a little bit more about that in a minute. And when there is when there is noise, this equality constraint, it's minimizing with a constraint A rho equals B. And then when the equality constraint in the noise case is replaced by an inequality constraint where A rho minus B in the L2 norm of this vector is less than or equal to some sigma, where sigma is usually unknown, but it indicates the noise level. Sparsity is not important in this approach. This is absolutely classical. We teach it in our classes. All the engineers know this backwards and forwards. And in order to get some decent resolution, you need some approximate orthogonality of the columns of A. And that is where a lot of the physics in the orthogonality means the inner product between the columns of A is the inner product between these Green's functions at different points of these Green's vectors, so Green's function vectors for different points Y in the image window. It is from this behavior of this inner product that you determine, you calibrate what the a priori pixelization of the window should be. And this is all very well known in the applied community. There's nothing, this goes back almost, not in this language, but in more physical language. It is well over 100 years that this has been known. Now, when you switch to L1, in other words, assuming that there is noise again, when you minimize not the L2 norm of the unknown sources, but the L1 norm subject to the same constraint, sparsity matters. And results started appearing in this about 15 years ago. And here I state the facts. A lot of people have worked on this. I mentioned some names in a minute. When there is no noise, in other words, the signals you receive have no noise. They're the exact, the model that I have over here. This is without any noise, this B here. And I'm only considering measurement noise. I'm not considering any other noise. Towards the end, I will say something about other kinds of noise. So the theory, which started about 15 years ago, in the L1 approach, recovers rho exactly provided the columns of A are close to orthogonal. There is an orthogonality relationship that actually depends on M, the number of the sparsity. However, even weak noise can make the L1 approach unusable. This is known in the literature, but it's not mentioned particularly prominently. In other words, in the earlier research in this area, the L1 approach, the noisy version was not studied very much. What people were much more interested in was this relationship between the orthogonality relation between the columns of A and the exact recovery, when the matrix A is not necessarily the one I showed, but it could be a random matrix and of very high dimension. And then there are some phase transition approaches. In other words, there's some phase transition results where, depending on this relationship between M and the orthogonality between the columns, when the dimension is large and the matrix A is random, you might not be able to, when do you recover? How sparse should it be under the circumstances so that you recover exactly? And when it's not sparse, then what happens? You don't recover anything. But the issue regarding noisy data, it was not so clear, although everybody who works in this field knows that this approach is very sensitive to noise, because simple numerical experiments immediately show that what happens. Now, what is the noise collector? The noise collector it's an idea. This is really an idea of Alex Novikov, and it took me a while to understand why this works. In fact, when we started out with this idea, I thought it wasn't going to work. It was really a surprise to me. So suppose, here's how it goes. Suppose rho is an m-sparse solution of the system, A rho equals B, with no noise. Okay, so suppose we go to the classical L1 theory. So this is the rho is that solution, the minimum L1 norm of the no noise problem, where the columns of A have unit length and they satisfy whatever orthogonality condition is necessary. The main result with the noise collector ensures that we can still recover the support of rho, of this no noise case, when the data is noisy, by looking at the support of rho tau, where rho tau is the minimum of these two things, a factor tau, which I will discuss, a weight tau, which I will discuss in a second, the L1 norm of rho, what the rho is what we are looking for, and then we introduce the L1 norm of n eta, some auxiliary variables, okay? And we augment the system to be not A rho equals B, but now it's A rho plus some other matrix C, that's the noise collector matrix, times this spurious variable theta, and B0 is the noiseless part of the data, plus some noise. Tau is a factor, is usually, it's order 1, it's actually a little bit bigger than 1. And then an appropriately chosen noise collector matrix C, which has a dimension n times sigma. Sigma is the number of columns of C. And this sigma is much larger than K. It's actually quite large. It has to be quite large. The minimization of this problem can be understood. One can think of this as a relaxation of the usual N1 formulation, as it works by absorbing all the noise and possibly some signal in C of tau. In other words, what we are saying is treat the noise as something you can estimate, the noise E, and you try to absorb it all into the C eta, while you try to arrange that the rho will really absorb all the signal from here. But you cannot, that's where the technical issues arise, and that's where the mathematics comes in to clarify. The fact that the sigma is very large, in fact, we thought it would be exponentially large compared to the size of compared to the n, the number of receivers. We thought that this would be totally unfeasible. It would be something perhaps of some theoretical interest, but not of practical interest. And then numerical simulations showed that this idea was actually remarkably effective, even when the sigma was not so large. And the numerical, then by looking more carefully at the numerical computations, everything could be done without much more difficulty, computational complexity, than the original problem. So here it is a case where you're not getting rid of the noise, you're estimating the noise, and you're getting rid of it by estimating it and throwing it out. Eventually, you don't care for it, but it cleans up the rho. Now, this allows for treating this L1 approach, getting extremely sharp results, especially getting the support almost exactly, in fact, I will say that. And then the noise can be very large at the same time. The columns of C can be chosen as uniformly random and independent on the unit sphere in n dimensions. So actually, we thought initially there was a better way of choosing choosing them to be maximally approximately orthogonal, but that is a little bit is computationally costly to do, and we don't really need it. The C can be chosen to be uniformly at random in dimension in the unit sphere in n dimensions. Think of n as becoming infinitely large. So the comment is that to denoise enlarge the system and estimate out the noise. Too big a computation? Not so. It doesn't, that's what we look carefully at the computation, and we explain how you can do the algorithm so that it doesn't really cost very much. So here are the numerical results. Everything is done in 2 dimensions. In other words, the array is really 1-dimensional, and the image window is not a box, but it's really a square. But the Green's function is in 3 dimensions. So it's just for computational, for visualization and computational simplicity. So this is where the sources are. This is what we recover. Actually, I will describe it, but this is really almost exact. So there are 12 sources located inside this box. I won't mention the physical parameters. It's set up with physical parameters in a microwave regime. This is not important here, but I will mention the numbers. So first of all, this is a multi-frequency imaging problem that involves 25 frequencies. The total number of data is N is 625. The total number of pixels, K, is 1621, much larger than 6. Sigma is 10,000. The noise collector has dimension 625 by 10,000. M, the number of sources, is 12. Now, here's what the interesting part is. The signal to noise ratio, which means the ratio of the L2 norm of the vector, the L2 norm of the vector B0 divided by the L2 norm of the noise, that is equal to 1. They're equal. The L2 norm of the B0 is equal to the L2 norm of E. It's as much energy in the noise as there is in the signal. And then you see that if you just do, without noise collector, if you do a straight L1 minimization, as I pointed out a little bit earlier, then you get garbage. And what is this figure here in the bottom show? It shows, it puts all the pixels lined up, 1681 of them here. And these red dots show the actual value of rho for the different pixels. And you get all this bunch of red, which is just noise, because the rho has very small support. Here's what the support is, that these green things, if you can see them, are the actual support. The red dots are the ones we recover by the method that I will now explain. So here we use the noise collector, but with a tau equals 1, it doesn't work so well. I said that the tau has to be bigger than 1. When this weight tau, I remind you what the tau is, it's this coefficient here. It plays a big role, actually. And then if the tau is 2, then you begin to see that it really cleans up this image, but doesn't get the strengths very well. The red dots are below the green ones. In the last one, you follow up, you do an ordinary L2 optimization on the support that you have found. The point here is that you got the support exactly. And when you do that, you recover the strengths immediately. So we have done this in many other situations, and it works remarkably well. And it's robust. So what are the results? There are 2 results, and then I should finish in about, I have another couple of minutes maybe. So consider A rho plus C eta equals B0 plus C, the problem at hand. Suppose now that B0 is 0. Suppose now that there's absolutely no signal, it's just pure noise. And that that the E over its norm is uniformly distributed, the noise is uniformly distributed over the sphere in Rn, the unit sphere in Rn. Fix a beta bigger than 1 and choose the sigma, the number of columns in the noise collector, C, to be n to the beta, some number bigger than 1. And they're supposed to be uniformly and independently chosen on the unit sphere. For any kappa positive, there are constants tau, that weight that goes into the optimization, and n0, such that for all n bigger than n0, rho sub tau, I remind you what rho sub tau is. Rho sub tau is the result of this optimization, okay? Then rho sub tau, the solution of equation 1, as I showed to you, is 0 with probability 1 minus 1 over n to the k. In other words, arbitrarily close to 1, depending on how. Remember that the kappa is you're choosing it. And it tells you how far out you have to go with the n, how many receivers you have to have so that you can do this. The important thing is to notice here is that you find there are no ghosts. In other words, you didn't put any signal and you don't find any. And that's a very good thing because it calibrates the system when there's only noise. And then the next theorem says that the recovery, what happens when rho is an m-sparse solution of the noiseless system, assume that kappa and beta and the noise collector are as in the previous theorem. Now, if the matrix A, the model matrix, its unit length columns satisfy this orthogonality condition, which is m dependent, sparsity dependent, then there is a weight tau and there is a number n0 such that for all n bigger than n0, the support of the rho tau, the result of the optimization, is inside the support of rho. In other words, you get the support, you get the support to be inside the correct support. And there's a slightly more elaborate result that I won't state, which says that if you sharpen the hypothesis a little bit, you can actually get the support exactly. So these are the results. It's basically a very interesting analysis that involves high dimensional probability analysis. And now I want to make some general comments. What else can be done with the noise collector? In another paper that we wrote about a year after this, and it just was accepted a few months ago, it turns out there's a completely different application. It was very surprising. It was discovered numerically that when your data is not a vector B, but the tensor product of B with its complex conjugate. In other words, you're not measuring the signals received, but you're measuring the cross correlations of the data. This is very important because that's basically what interferometry is. In other words, sometimes you can't even measure the B, but you can measure this quantity here, B, tensor B bar, because that means that you can measure directly correlations through an interference, through interferometry. But when you formulate a system, then you have to tensorize. Everything has to be more or less squared. And the dimensions become incredibly large. For example, now the unknown is rho tensor rho bar, which is n by n, it's n square dimensional. So the dimensions are huge. It turns out, but you only need the diagonal of this tensor. You don't really need everything. And usually the rho is, the strength is usually negative. It doesn't have to be complex. It's not negative. So the idea was to treat this the off diagonal part of this, which we don't really need, as noise, and use the noise collector idea in this. And it turns out it works. It was a complete surprise to all of us. And so the noise collectors now plays the role of a complexity reducing, of computational complexity reducing technique. It's not a denoising anymore, although you can put noise in there too. But it just says that you can go to imaging with cross correlations at essentially no extra cost than using directly the signals received. Okay, this is my last slide. So here's what we cannot do. We cannot do imaging in random media, where actually the model matrix A is itself now random. But there is hope. I spent, in the last 20 years, a tremendous amount of my time thinking about how to do this. We've made some progress. We have studied waves in random media. Here's my contact with Rafail. For the first part of my career until the mid-90s or so, I've studied waves in random media. And for a long time, I was doing this where averaging over the random medium was absolutely the essential thing to do. You didn't want to know the details about the medium through which the waves were propagating. And that's when I ran across the work of Rafail in the 1960s for averaging for stochastic differential equations, which had at the time really surprised me because it was it had an originality and a contact with applications that I didn't expect. Although, of course, averaging was known for nonlinear oscillations and for other problems, was very, very well known in the physics community. There was nothing known about it in random media, but I'm not exactly sure how he was motivated about it. But for the kind of applications that I was interested in, it was a very, very good result to start with, and it was the only result of its kind at the time. However, when in the 90s I started moving into imaging, it turns out that averaging of the type that homogenization, averaging, all these ideas were actually the enemy of imaging, because they destroy resolution. Any kind of averaging takes away resolution. So the tool to use in imaging is thresholding. You just simply get rid of the noise by thresholding. And that's what we did at first using coherent interferometry, which I won't mention. And then we switched to the L1 methods. The L1 methods are methods that really focus on thresholding. And so the noise collector actually goes a step further. It says, don't try to threshold, just simply estimate the noise and throw it out. That's my last comment. Thank you, Rafail, and may you reach 100 or 120, as it was mentioned there, and hope to see you again soon.
Thank you very much, George, for the very interesting and exciting talk. And it's my pleasure to announce the talk by Rafail Khasminskii, Limit Behavior of RK-90 Problem for Parabolic Equations with Periodic Coefficients.